A sloth, a donkey, and a curious human. Send a prompt and see what they're doing. One hits record with a question on his mind. Two brothers pick it up, see what they find. Corn takes his time, Herman's got the facts. Back and forth, they never hold back. My weird prompts, come on in, that's where we begin. My weird prompts, glad you're here.
This episode was generated using artificial intelligence. Please verify facts.
My Weird Prompts is a community-driven initiative exploring how AI can fuel curiosity and uncover the fascinating ways our world works. GPU compute for this podcast is generously provided by Modal. Learn more at modal.com.
I was reading a report the other day about modern air defense, and there was this one statistic that just stopped me cold. We are regularly seeing situations where a defensive battery fires a missile, costing $2 million to intercept a drone that was cobbled together for about $20,000. That is a cost-exchange ratio of 100 to 1. Today's prompt from Daniel is about the Iranian UAV ecosystem, and it really hits on why that lopsided math is becoming the defining challenge of modern warfare. We are talking about a fundamental shift from the era of precision-guided munitions to what military theorists are now calling swarm-as-a-service doctrine.
It is the ultimate asymmetric headache, corn. I am Herman Poppleberry, and I have been diving deep into the technical specifications of the Shahed and Mohajer families because, on paper, these things look like toys. If you saw the engine of a Shahed 136 sitting on a workbench, you would probably think it belonged to a high-end lawnmower or a go-kart. But in a tactical environment, that perceived simplicity is actually a highly evolved engineering choice. It is not that they cannot build something more complex, it is that they have realized complexity is the enemy of scale.
That is what I want to get into. There is a tendency to look at these Iranian drones and call them primitive, because they use wooden propellers or off-the-shelf electronics. But if they were actually primitive, they would not be causing the kind of systemic stress we are seeing on sophisticated integrated air defense systems. What is the design philosophy here? Is it just cheapness? Or is there a deeper technical logic to using low-tech components?
It is a deliberate optimization for what military theorists call attrition-based saturation. To understand this, you have to look at the primary case studies, the Shahed 136 and the Mohajer 6. When you build a traditional cruise missile, like a Tomahawk, you are building a Ferrari. It has a micro-turbojet engine, sophisticated terrain, contour matching, and costs millions. Iran looked at the problem and realized that for the price of one Ferrari, they could build 200 mopeds with explosives strapped to them. The moped in this case is the Shahed 136. It is a suicide, or loitering munition, which is fundamentally different from a cruise missile. A cruise missile is designed to be fast and stealthy through high-end materials. The Shahed is designed to be stealthy through its sheer insignificance to a radar's processing logic.
You call it a moped, but a moped is easy to hear and easy to see. If I can hear it coming from miles away, why is it a problem for a radar system that is designed to track stealth fighters or ballistic missiles traveling at Mach 5?
That is the core paradox. Most modern radar systems, especially the high-end ones used in Patriot batteries or Aegis destroyers, are designed to filter out clutter. They use something called the Doppler shift to distinguish between a dangerous threat and a bird or a cloud. This relies on radial velocity, the speed at which an object is moving toward or away from the radar. If something is moving at 300 miles per hour, the radar says, "Aha, that is a missile." But these drones often fly at 90 or 100 miles per hour. That is very close to the speed of some large birds or even fast-moving ground traffic if the radar is looking at a certain angle. In many cases, the signal processing in the radar literally ignores the drone because it thinks it is biological clutter. It falls into what engineers call the Doppler notch, where the target's velocity is too low to be flagged as a threat by the automated systems.
So, we have built these incredibly expensive digital filters to find the fast stuff, and the Iranians are just driving right under the speed limit. It reminds me of that scene in every heist movie where the guy walks slowly past the motion sensor because it only triggers on rapid movement. But surely the thermal signature is a giveaway? A combustion engine gets hot.
It does, but compare a 50 horsepower piston engine to a jet turbine. A jet turbine is a literal blowtorch. It creates a massive infrared plume that heat-seeking missiles can lock onto from miles away. The engine in the Shahed is the MD-550, which is a reverse-engineered version of a German Limbach L-5550. It is a 50 horsepower, 4-cylinder, 2-stroke engine. Because it is air-cooled and relatively small, and because it is flying at 2,000 feet, the atmospheric cooling and the small displacement mean its thermal signature is tiny compared to a traditional missile. It is not invisible, but it is quiet. Enough in the infrared spectrum that older MANPADS, those shoulder-fired missiles, often have a hard time getting a reliable lock until the drone is practically on top of them. And by then, it might be too late.
Let's pivot from the hardware itself to the nightmare it creates for radar operators. While the thermal signature is low, the radar cross-section is the real nightmare, right? I have seen estimates that a Shahed has a radar cross-section of 0.01 square meters. For people who do not speak radar, how small is that actually?
It is roughly the size of a large crow or a seagull. And remember, it is not just the size, it is the material. A lot of the airframe on these drones is made of carbon fiber or glass fiber composites. These materials do not reflect radar waves nearly as well as the aluminum or titanium skin of a fighter jet. We are even seeing evidence of poor man's stealth in the newer models. They use honeycomb, structures inside the wing sections. This isn't just for weight. Those honeycomb patterns can be tuned to trap certain radar frequencies. When a radar wave hits a honeycomb structure, it bounces around inside the cells rather than reflecting back to the receiver. It is an 80-20 solution. They are getting 80% of the stealth capability of a high-end coating for about 1% of the cost. So, you have a target that is the size of a bird, moving at the speed of a bird, and made of materials that look like a bird to a radar beam. If you are an operator sitting in a command center, your screen might be showing dozens of flickers that look like environmental noise, when in reality it is a coordinated strike package.
I imagine the navigation system adds another layer of resilience. We always hear about GPS jamming in conflict zones like the Middle East or Eastern Europe. If I'm using a $20,000 drone, I'm probably using a commercial-grade GPS chip, the kind in my phone. If the military jams that signal, does the drone just fall out of the sky?
Not at all. This is where the Iranian engineers have been very clever with redundancy. They use multi-constellation GNSS receivers, so they are pulling signals from GPS, GLONASS, and Galileo simultaneously. But more importantly, they have integrated basic inertial navigation systems, or INS. These are gyroscopes and accelerometers that track the drone's position based on its last known starting point and its movement. It is not accurate enough to hit a specific window from 500 miles away on its own. INS drifts over time, but it is plenty accurate to keep the drone on course until it exits the jam zone and can reacquire a satellite signal. It is essentially dead reckoning through the interference. It is like driving through a tunnel. You might lose your signal, but you know you are still heading north at 60 miles per hour, so you can estimate where you will pop out on the other side.
But what about the final terminal phase? If the goal is to hit a specific oil refinery or a power substation, dead reckoning is not going to cut it.
For the higher-end models like the Mohajer 6 or the newer Shahed variants, they are adding optical correlation. They have a camera in the nose, and the onboard processor compares the live video feed to satellite imagery stored in its memory. When it sees a shape that matches its target, it locks on. This is purely passive. There is no radar emission for the defender to detect, and no radio signal to jam. It is just a computer looking at the ground. It is the same technology used in cruise missiles for decades, but it has been miniaturized and commoditized to the point where it fits on a circuit board the size of a deck of cards. Some of the newest models we are seeing in early 2026 are even using visual odometry, where the camera looks at the ground, identifies landmarks, and calculates movement based on how those landmarks pass by. You cannot jam the ground.
It feels like we are seeing the democratization of precision strikes. It used to be that only a superpower could hit a target 300 miles away with 10-meter accuracy. Now, anyone with a decent machine shop and access to a global supply chain can do it. You mentioned the Mohajer 6. How does that differ from the suicide, loitering munitions like the Shahed?
The Mohajer 6 is more of a traditional multi-role UAV. It looks a bit like a smaller version of the American Predator. It can carry out reconnaissance, but it also has hardpoints for small precision-guided bombs, specifically the KM series. The interesting thing about the Mohajer is its endurance. It can loiter for 12 hours. In a tactical sense, Iran uses these as pathfinders. They will fly a Mohajer near the edge of an adversary's air defense bubble to see which radars turn on and where the gaps are. They are mapping the electronic order of battle in real time. If you're wondering how this fits into the broader regional picture, we actually covered the strategic doctrine in episode 945, The Ring of Fire. These drones are the eyes for the heavy hitters.
Which leads us to the tactical nightmare of the swarm. If I am a commander of an Iron Dome or a Patriot battery, and I see one Shahed, I can kill it easily. But what happens when 50 of them come at once from different directions?
That is the saturation problem. Every air defense system has a finite number of fire control channels. This is the radar's ability to paint a target and guide a missile to it. If a battery has 4 channels, it can engage 4 targets simultaneously. If you send 5 targets, the 5th one gets through. Now imagine you send 80 drones. The system is physically overwhelmed. It runs out of interceptors, or the radar's processor hits a ceiling where it cannot track that many discrete objects moving at low altitudes through ground clutter. We saw this play out in the True Promise 3 and 4 operations. The drones go first. They are slow, so they are launched hours in advance. Their job is to soak up interceptors, force the defensive radars to stay active, and essentially distract the system. Then, just as the drones are reaching the target area, the cruise missiles and ballistic missiles arrive. By that point, the air defense operators are exhausted, their interceptor inventory is depleted, and the radar screens are a mess of overlapping tracks.
It is like a coordinated DDoS attack, but in physical space. You are flooding the server with garbage requests so the legitimate traffic, or in this case, the more dangerous missiles, can slip through. We talked about saturation tactics with cluster munitions in episode 1093, but this feels even more insidious because the drones are smart. They can be programmed to fly circuitous routes, coming in from the sea or behind mountains to avoid detection until the last possible second.
They can even be programmed to loiter. Imagine a drone that flies to a specific waypoint near a target and just circles in a valley for 20 minutes until it receives a signal or until a timer goes off, and then it joins a larger group for a synchronized strike. That level of temporal coordination is something that used to require a massive command and control infrastructure. Now it is just a few lines of code in a flight controller. And think about the psychological impact. If you are a civilian or a soldier on the ground, and you hear that moped sound in the sky, you know an explosion is coming, but you don't know where. Because they are slow, the alarm can last for an hour. It creates a sustained state of anxiety that a fast-moving missile strike doesn't. It is a form of psychological warfare that is built into the acoustic signature of the engine. I have heard people call it the screaming Mimi of the modern era, referencing the German rockets from World War II. The sound itself is a weapon.
Let's talk about the manufacturing side. One of the things that makes this ecosystem so resilient is how decentralized it is. We are not talking about one massive factory that can be taken out with a single strike. How is Iran producing these at such high volumes despite decades of sanctions?
It is a masterclass in sanction-busting logistics. They have spent years building a network of front companies to buy dual-use components. A servo motor for a remote-controlled plane is not a weapon. A spark plug for a small engine is not a weapon. A CMOS camera sensor from a doorbell is not a weapon. But when you put them all together in a carbon fiber shell with a few pounds of high explosives, you have a strategic asset. They have also leaned heavily into modularity and three-dimensional printing. Many of the internal brackets and small components in the newer Shahed variants are 3D printed from high-strength polymers. This allows them to iterate the design almost weekly. If they find that a certain component is failing in cold weather, they can change the CAD file and have a new version on the assembly line the next day. It is agile development for munitions.
That has to be incredibly frustrating for Western intelligence. You are trying to track a supply chain that looks like a hobbyist's shopping list, but surely there are choke points. Is there anything in these drones that Iran absolutely cannot make themselves?
The high-end microprocessors and the high-precision inertial measurement units are the two big ones. Most of what we find in downed drones are chips from major Western manufacturers. They are the same chips you would find in a high-end washing machine or a car's infotainment system. You cannot stop the global trade of these components. Even if you stop a shipment to Tehran, it just goes to a third-party distributor in a neutral country and then gets smuggled across a border. The scale of the global electronics market is simply too large to police effectively at this level. This is why we see the same components in drones used by non-state actors in Yemen and elsewhere. The technology has leaked out completely.
So we have a low-cost, low RCS, highly redundant system that is designed to overwhelm defenses through sheer numbers. It is easy to build, hard to track, and expensive to shoot down. If you are an air defense engineer, where do you even start? How do you fix that cost-exchange ratio?
You have to move away from kinetic interceptors. If you are using a missile to kill a drone, you have already lost the economic war. The future of countering this threat lies in two areas: directed energy and electronic warfare. Directed energy means lasers and high-power microwaves. A laser shot costs about the price of the electricity used to generate it, maybe a few dollars. If you can keep a laser on a drone for 3 seconds, you burn through the plastic housing or fry the optical sensor and the drone crashes. No $2 million missile required.
I have seen some of the testing for those systems, like the Iron Beam in Israel. It looks promising, but the problem is dwell time, right? If you have 50 drones and it takes 3 seconds to kill each one, that is 150 seconds. In that time, half the swarm has already hit the target.
That is the limitation. Lasers are line of sight and can be affected by weather, smoke, or dust. That is why high-power microwaves are actually more interesting for swarm defense. A microwave weapon can emit a wide cone of energy. Anything with a circuit board that enters that cone gets fried instantly. You could potentially take out 10 drones with a single pulse. It is the ultimate electronic shotgun. We are seeing a massive push to deploy these on mobile platforms, basically putting a giant microwave oven on the back of a truck to create a no-fly zone for electronics.
And what about the electronic warfare side? We talked about the drones being resistant to GPS jamming, but they still have to communicate sometimes, don't they? Or at the very least, they have internal clocks and sensors that could be messed with.
Right, and that is the cat and mouse game. If you can flood the area with spoofed GPS signals, you might be able to convince the drone it is 50 miles away from where it actually is. If the drone believes the spoof signal more than its internal sensors, it will fly itself into the ground or off into the desert. But as we discussed, visual odometry and INS are making that harder. We are also seeing a resurgence of old-school, anti-aircraft guns like the Gepard because they are incredibly efficient at killing drones. A burst of 30mm shells costs a few $100s. That flips the cost-exchange ratio back in favor of the defender. A missile is fast, it has a huge warhead, and it can penetrate much heavier defenses. Drones are for saturation, missiles are for the knockout blow. You need both.
It feels like we are reaching a point where the offense has a massive structural advantage. In the 20th century, defense was about building a bigger wall or a better radar. In the 21st century, offense is about building 10,000 cheap, smart things that can find the one hole in your wall. It is a fundamental shift in military philosophy. We are moving from quality over quantity to quality assured quantity.
The Iranian UAV program is the most visible example of this, but we are seeing it replicated everywhere. It has effectively neutralized the safe haven of the deep rear. If you are within 1,500 kilometers of a launch site, you are on the front lines. The strategic depth that countries used to rely on is evaporating. If a drone can fly for 12 hours and hit a specific substation, then your entire national infrastructure is vulnerable 24/7.
That is a sobering thought. I want to go back to the engineering of the airframe itself. You mentioned carbon fiber and composites. Is there any evidence that they are using actual radar-absorbent material, or is it just the shape and the base material doing the work?
It is mostly the shape and the base material, but the delta wing design of the Shahed is inherently low RCS from certain angles. Because it doesn't have a vertical tail fin, there are fewer 90-degree angles for radar waves to bounce off of. It is a very clean aerodynamic shape. And because they are disposable, they don't have to worry about long-term maintenance or stealth degradation from weather. You just build it, launch it, and it either hits the target or gets shot down. Either way, its job is done. The West spent 40 years perfecting the defense against the heavy cavalry, the high-speed jets and missiles, and then someone showed up with 1,000,000 angry bees.
So, as we look forward to the rest of 2026 and beyond, what is the next step for this tech? We have seen the Shahed and the Mohajer. What is coming out of the Iranian labs now?
We are seeing jet-powered versions of the Shahed, like the Shahed 238. This increases the speed, which makes it harder to hit with machine guns, though it does increase the thermal signature. We are also seeing loitering drones that can communicate with each other to perform true swarm maneuvers, where the drones coordinate their attack angles autonomously without a human in the loop. If you have 50 drones that can talk to each other and decide which one will distract the radar and which one will strike from the blind spot, that is a whole new level of threat. That brings up the AI component. If you can put a low-power AI chip on these things, they don't even need a signal from home. They can just be told, go to this area and find a tank, or find a radar dish.
That brings us to the democratization of precision strike. How this tech is proliferating to non-state actors is perhaps the most dangerous part. If a non-state group can launch 100 smart drones, they have the striking power of a small air force.
And that technology is already here. We are seeing it in commercial drones used for light shows. Scaling that to a military application is just a matter of hardening the hardware and refining the algorithms. The era of the dumb suicide drone is ending. The era of the autonomous swarm is beginning. And that is a challenge that our current air defense systems are simply not built to handle. Our air defense doctrine was built around intercepting Soviet bombers and high-speed cruise missiles. We built big, powerful radars and big, fast interceptors. We didn't build a fly swatter because we didn't think flies could sink a ship or destroy a power plant. Now, we are scrambling to build those fly swatters. Whether it is laser systems, electronic warfare bubbles, or even just putting more machine guns on trucks, the entire architecture of air defense is being redesigned as we speak.
It is a fascinating example of how a technical constraint, in this case, Iran's lack of access to high-end jet engines and advanced materials, led to a tactical innovation that has fundamentally changed the global security landscape. They couldn't build a Tomahawk, so they built something that made the Tomahawk's defenses irrelevant. It is the judo of military engineering. You use your opponent's strength, their reliance on sophisticated, expensive sensors against them. The more sensitive the radar, the more likely it is to be confused by a swarm of bird-sized targets. The more expensive the interceptor, the faster the defender goes bankrupt.
It is a brilliant, if terrifying, bit of strategic engineering. It is the revenge of the good enough. And in the world of Iranian UAVs, good enough is proving to be a world beater. We need to watch for how these systems integrate with ballistic missile doctrine, which we covered in episode 918. When you combine the swarm with solid fuel ballistic missiles, you get a multi-layered attack that is almost impossible to stop completely.
Well, that is a perfect place to wrap up the technical deep dive. It really changes how you look at those grainy videos of drones flying over cities. There is a massive amount of engineering and strategic thought behind every one of those moped sounds. It's not just a cheap drone, it's a piece of a much larger, very calculated puzzle.
It is a testament to the fact that you should never underestimate an engineer with a limited budget and a clear goal. The era of the expensive interceptor might not be over, but its dominance is certainly being challenged.
Before we get out of here, I want to give a huge thanks to our producer, Hilbert Flumingtop, for keeping the gears turning behind the scenes. And a big thanks to Modal for providing the GPU credits that power this show and allow us to run the models we use for our research.
If you found this dive into UAV tech interesting, we have a whole archive of similar deep dives at myweirdprompts.com. You can find our RSS feed there and all the different ways to subscribe.
We are also on Telegram if you want to get notified the second a new episode drops. Just search for My Weird Prompts. This has been My Weird Prompts. We will catch you in the next one.
See you then.
This episode was generated using Gemini Flash 3. Text-to-speech engine was Chatterbox.
Thanks for listening to our show.